So we start off with a definition, def, and actually I write better if I go slower, so I'll really try to chill here. Okay, so a graph consists of two sets. So the first is a finite. I'm putting finite in parentheses because this isn't actually required. There is the notion of an infinite graph, which may come up. That's not the focus of this class, but there's some wild stuff that happens when you do allow that. So most of the time, we'll be working with finite objects here. Okay, so a finite set of vertices, okay, denoted with the set V here. I'm going to be defining three terms simultaneously here, which doesn't totally make sense. But the word vertices is just the name of this set V. It doesn't have any property. It's just a collection of things. And a set E of two element subsets of V. Okay, let me just emphasize here. These are sets, and sets have no order to the elements here. Okay, so I'll just add unordered. Okay, unordered elements. So two element subsets. So you grab two things from the vertex set, and that forms an edge, what's called an edge, so called edges. Okay, that's all a graph is. And in some sense, this definition is sort of unsatisfactory, and we'll very rarely think about it in this way, but this is the formal definition. So what is a graph? It's just a collection of vertices, or sometimes points, and a collection of pairs of points. Some of the pairs of points, right? There's a bunch of different pairs you can choose. You may choose some, you may not choose any. So let me write a little more words and then we'll draw pictures. That's a big component of this class. Graph theory is wonderful because you can draw pictures of everything and it really helps your intuition. And pictures are not forbidden in the homework. When you write homework solutions, if you draw pictures to help motivate the argument or even give the argument, I encourage it. It makes it much easier to read. And it's not, there is a slight issue with rigor sometimes if you make assumptions in your picture, so you need to be careful, but it's absolutely allowed, okay? So if we're working with a specific graph G, so for a graph G, we denote the vertices. So we'll use verts this all the time for vertices. So the vertices, the set of vertices is just denoted by V of G. So if we're talking about two graphs simultaneously, V of G is the vertex set of G and V of H is the vertex set of H, okay? So the vertices are V of G and edges are E of G, okay? It's just so we can keep them separate here, okay? Let's look at some examples though of some graphs here, okay? So usually with graphs, we won't even think about these things as sets when we're defining them initially. So like, let me just draw some pictures. So usually what we do here is draw the vertices. Like I use the term points because that's exactly what how they'll be represented like in a drawing here. So these are the vertices. This graph has 5 vertices and then it has some edges, right? And what's the easiest way to denote, to identify a pair of points, a pair of vertices? We draw a line between them, right? I'll draw a line between them if there's an edge. So that line means that this vertex and this vertex is a 2-element subset, right? It's one of the 2-element subsets included in this graph. Okay, this one, let's say it looks like this. And maybe there's that and that. There's our graph. And let me add one more edge to make a point as well. There's this edge here, okay? So there's a graph. You notice not every pair of vertices is joined by an edge. We could continue to add edges if we wanted to, but this specific example doesn't have everything. It has these. And one thing to emphasize, this last edge I drew was like a curved line. There's no geometry in graph theory. Actually, one occasion there will be. That's kind of a cool thing, but there's generally no geometry. And so curved lines that, let me even add another one here. Let's add this line here. Oops, this edge. You see how it crosses here? That has no meaning in graph theory as well. The point of that line is just to emphasize that this point and this point are included together in an edge. It's just a representation here, okay? We could represent this in another way, which is much less useful, but we could say, let's be a little more formal here. So let's give names to these vertices. Call this A, B, C, D, and E, okay? That would mean the vertex set of this graph is just A, B, C, D, and E, right? We said that it's 2 sets. And the edge set, well, I'm not going to do all of this, but the edge set is a set of pairs, a set of 2-element subsets. So it's a big set here. And what does an edge look like formally? What is it? What is the object? Actually, if someone wants to unmute and answer, that's more than welcome. I know it's a trivial question, but what is an edge? Like formally, according to the definition, what is the object?
2-element subset of V.
Yes, exactly. It's two elements. So we have a number of edges here. So let's say the 2-element subset A comma B, that's an edge, right? And what's another one that's here? A comma C and A comma E and so on. I'm not going to write all these out, right? And so on and so forth. You can see that this formal definition is horrible, right? This contains the same content as this picture here. But if I write this down and tell you to tell me things about this graph, you won't be able to do it until you draw it, right, basically. This, of course, formal definition is quite useful when working with graphs with a computer, right? I mean, this is actually how you would encode that information or something like it. There's other ways too. The picture is not so useful for a computer. Yeah, we will almost always work with a picture. If I'm talking about this graph here, I would never write all this stuff down. It's hard to work with, it's lengthy. One thing, occasionally we will see these things. One thing we will do, certainly we'll make this the following abuse of notation. If I wanted to list the edges, I'm not going to list pairs like this. I'm just going to write AB, AC, AE, and so on. That's a little bit nicer way to write things. Here you have to be careful though, although it will come up later. These are unordered pairs, right? AB and BA are the same content. That's the same edge. Down here, this seems to emphasize A comes before B, but this is just the convention we use in graph theory. This doesn't have any particular meaning that A comes before B, that there's a direction or anything like that, okay? All right, let me draw a couple more graphs here. Let's see if we can get this to work. This is what I like about this. I can kind of like keep some stuff on the screen. Okay, so let me just draw 2 more examples. I'm not gonna write out the details here, but say we got 5 points again, and let's say we've got all possible edges. This will be one of your early homework exercises to determine how many edges this has. All right, so I got 5 vertices and all pairs are joined here by edges. This is actually what's called a complete graph. Has a special name. We'll learn many names. Many graphs have certain special names. There are all kinds of classes of graphs and so on. Maybe one more example here. Let's even do one that's maybe you've seen before. You can see where this is going. Right, so that's a graph as well, right? I have a bunch of points here, and each has 2 or 3 edges. 2 edges coming out of here, 3 coming out of all of these, 1 coming out of down here. But this is usually called a binary tree, which is a pretty typical data structure in computer science, for instance. It's interesting for any number of reasons, but that's a graph as well, okay? All right, so we have to add a couple little more details that, yikes, I don't want that. So there's the notion of a multigraph as well. It's a slight generalization of a graph, and usually we will not focus on it, but occasionally there are opportunities or instances where we want a slightly more general definition. And it's written out a little more formally in the notes and certainly in the books, but let me just give a rough idea what I mean by a multigraph. Okay, so multigraph, it's essentially a graph where we allow 2 additional properties. First of all, we allow edges to have duplicate edges, okay? So let's say multi-edges are allowed. Whatever that means, I'll draw a picture and then it'll be clear. Okay, let's literally draw the picture. So here's a graph here. Say we have 3 vertices and 3 edges. And I also add this edge here. But that edge already was there, right? Between this vertex and this vertex, I now have 2 edges. I could even add more. Let's add a 3rd one here. By the formal definition of a graph, that makes no sense because the collection of edges is a set. Sets do not have duplicates in them, okay? So in a multigraph, the edge set, we just allow to be a multi-set, so you can have repetitions here, okay? Sometimes we call these things parallel edges, right? For a topic with no geometry, we definitely borrow from geometry a lot. These are not parallel in the geometric sense, but they are duplicates of one another, okay? So that's what a multi-edge is. It's a duplicate of an edge. Sometimes this is handy. And then we also allow loops, okay? Also loops. So what's a loop? A loop is a special type of edge that just starts at a vertex and ends at the same vertex, okay? So this is a loop. All right. So those are allowed in multigraphs. Again, most of the time we will not allow these two situations, but sometimes it's convenient to allow them. And moreover, most of the theorems will prove in the class, most but not all. Most will hold not only for graphs, but for multigraphs simultaneously, okay? That's something to keep in the back of your mind. When it's important that a theorem holds for multigraphs, I'll emphasize it because we'll be using that property. But if it doesn't, then I won't emphasize it. But it's always a good thing to have in the back of your mind about, does this work for multigraphs as well? Okay. All right, good. So let's, what do I got next here? Oh yeah, okay, so this little bits in the notes, maybe I won't write the whole thing out, but like why do we even care about graph theory? How did it come about? So just personally, I'm a graph theorist mostly from like a theoretical point of view, and I'll actually maybe talk about some of my research type stuff later on in the class because you might find it interesting. But graph theory is interesting in its own right. Just understanding these graphs and learning properties about them is a joyful experience anyway, at least if you ask me. I mean, I'm biased, but the subject came about, like most subjects in mathematics, through various applications. And this is pretty evident these days. In the early days, it was less clear that, like, you know, network structures were less obvious, but now that's all we talk about all the time, right? I mean, almost every object that we encounter in science and in industry and things like that can be modeled in some fashion as a type of network, right? Where you have various things and connections between those things. And that's exactly what a graph is. So graphs are great at modeling real world objects. And there's like this huge list of them. I mean, you can come up with as many as you want, but let me just mention a few. Maybe I'll scribble down a couple. I don't want to write all these down. This comes from another book by a very, very famous graph theorist here. So graphs, oh my goodness. Graphs can model many things, but let's look at a couple examples. So one obvious one is, like, you know, the internet with, okay, I spelled that wrong, but computers and what he calls data links. This could be just, you know, connections over your Wi-Fi or literal wires, or, you know, connections between servers and so on. Very obvious network, one we think about all the time. The web, right? So like the World Wide Web is made up of what? It's made up of websites. So sites are your vertices, they're your points, and two sites are joined if maybe there's a hyperlink between them or something like that, and hyperlinks. This one's actually a little bit interesting here because hyperlinks are don't tend to be two-way, right? And so it's not really like an edge, it's kind of like one direction to another, but there are other models of graphs that make this work here. The most popular these days are social networks. And these have a very, very obvious graph structure. Facebook's sort of the easiest example, right? You've got users on Facebook, and friendship on Facebook at least is mutual, right? And so that forms an edge. Like you can model the entirety of Facebook by as a graph, right? You just have all the points, and they do these types of things and do analysis on that. Edges are just friendships. Twitter's a little more interesting because it's one directional. And so you can follow people, and that gets an edge sort of in one direction, which is something we call a directed graph, which you can probably already figure out what that is, but that'll be a subject that we'll discuss later in the class. Chemical networks with atoms and chemical bonds, biological networks like the brain, neurons and synapses, transportation networks, that's one of my favorites, where you have airports and direct flights between airports. All this stuff can be modeled as graphs. And understanding how to efficiently search on a graph with various algorithms, that's a major topic of computer science and of graph theory. And understanding what properties in a graph give rise to other properties in a graph can be very useful for understanding, you know, the architecture of these systems and stuff. So that's sort of the motivation of graph theory in the first place. I won't focus a lot on applications here. We will see a number of algorithms though, some of which you probably already come across. The focus in this class with algorithms more will be proof of correctness rather than analyzing speed and things like that. That's maybe for another course, okay? All right, so that's maybe like a little motivation if you needed one, but you did register for this course already, so anyway. All right, so let's get to a couple definitions, and then I want to prove at least one theorem, maybe two here if time allows. Okay, so, and along the way when I give definitions, I'll almost always try to give a little drawing to further explain what it is, But a lot of these definitions are very, very simple, and even the word just tells you what the definition is. Like we really like to use, good metaphorical language in graph theory, and so it's usually like, oh, that must be that, and then it's usually correct. But okay, so let's start off with, let's just write definition here. I'll define a few things here though. Okay, so two vertices, U and V, are adjacent if they're joined by an edge. So if joined by an edge. And that edge being UV, right? That's the only edge that can join U and V. So we just call them adjacent if there's an edge between them. We don't even need the term adjacent because we can just say that whether there is or isn't an edge between them, but it's very convenient to use that term there. All vertices adjacent. So you're going to see my abbreviations: verts, ADG, J for adjacent, to a vertex V are its what we call neighborhood. There, it's neighborhood. Okay. So maybe as an example here, here's my vertex V, and its neighborhood are all these vertices that are joined to it, that are adjacent to it. Okay. Maybe there's a vertex over here, maybe some over here. It's just these. This is the neighborhood of V. Call this N of V is the notation there. So denoted N of V, that's its neighborhood. Very clear term. Neighborhood doesn't include the vertex V itself unless there's a loop, right? If we have a loop, then you're in your own neighborhood because you're joined to yourself by an edge. That usually doesn't come up. Sometimes we use the term closed neighborhood to include the vertex, but that's extraordinarily rare. So that's the neighborhood. And then we have this term of incidence. So two edges are incident if they're touching each other, meaning if they share a vertex. So if they share a vertex. Okay, so for example, this edge here and this edge here, this is edge E and F. Usually we give edges their own names as well, even though they're composed of two vertices, but sometimes there's no reason to name the vertices. And so we could call the edges E and F here. These two are incident, whereas, where am I? E and like G here, those are not incident. They don't share a vertex, okay? We'll also use incident for a vertex and edge pair. If a vertex is in an edge, then we say those two objects are incident as well, okay? Anytime things are shared, they're incident. In fact, incident will be used for all sorts of different objects that occur in graphs, okay? So a vertex and edge, this pen has like buttons on it, and I disable them, but if I press them, it doesn't write on the screen, and it's like extraordinarily annoying. So if you hear me like wanting to swear, it's because I'm pressing this button. So, all right. A vertex and an edge are incident. So it's an abusive notation, right? This term is used for two things. If the vertex is in the edge, right? So like this vertex V here is incident to E and incident to F. Okay. Just terms to make things easy to talk about. Okay. All right, so those are incident there. And then maybe the most important definition, certainly for the first, for today, is the degree of a vertex. Okay. So the degree of a vertex V is the number, there's a number of ways to define this. It's the size of the neighborhood, or it's the number of incident edges. I'm going to say number of incident edges. So is number of incident edges to V. Okay. So here's V, and these are the number of edges incident to it. And so the degree of V, so denoted, we just use this little d of V for the degree of V. Or if we're working in a specific graph G, sometimes we'll say d sub G of V, just to emphasize we're talking about the degree of V in the graph G. Sometimes we're working with two graphs simultaneously, and even though we have the same vertex, maybe we've transformed one graph into another, and we want to distinguish the degree between the two. Most of the times, the subscript will be excluded, though, when it's clear from context what we're talking about. So in this case, d of V equals 4, okay? Now, maybe someone can tell me here, why did I talk about number of incident edges and instead of talking about the size of the neighborhood, which in this picture appear to be the same? Why did I make the distinction? Why say incident edges?
Does a loop count as an incident edge?
Okay, that's very good. I was gonna get to that in a moment. That is actually even more problematic. So hold that thought for 1 second, but I will answer that. What's another object? You're on the right track there. That may cause issues between neighborhood and incidences.
In the same vein, parallel edges can be a problem.
Yeah, exactly, right? So if I added a parallel edge here, I mean, this is a definition, so we can decide what it's going to be, for us. We could just say it's neighborhood, but then here the neighborhood's 4, but there's 5 incident edges. So that's why we made this distinction of incident edges. So in this case, it's 5. But your question about loops is well taken. In this case, we should have loops contribute 2. Okay, and so let me even say in words another definition. I just don't want to write it out because it's so awkward for ordinary graphs, but it does hold for multigraphs. So let me explain here. So if I have a loop, it's only 1 incident edge, so it should only contribute 1. But the true behind the scenes definition here really should be the degree of a vertex is how many times it's the end point of an edge, right? And then that would capture 2 from a loop and 1 from each of these guys going out. Okay, so that's like the true definition. But when you're talking about a graph, the edges incident is equal to the number of edges, the size of the neighborhood is equal to the number of times it's an endpoint in the graph. It's only in multigraphs with loops where you have to worry about these distinctions here. And so almost never will it matter that the loop contributes 2. I can only think of like 2 places in the whole text. So most of the time that's not important, but like in the notes I've written out as a footnote, like the true behind the scenes definition, okay? And there's a reason for that. A lot of the theorems don't make any sense unless you make the loop contribute 2. So I'm going to put this. So loop adds 2. So this definition is kind of a hack, right? It's like the number of incidents edges plus extra 1 for each of the loops. Kind of annoying this way, but I hope you understand what I'm getting at here. Okay. Most of the time, it's just the size of the neighborhood. Okay. All right. So that's the degree. Maybe I won't write them out. But if you're looking at a graph, the maximum degree and the minimum degree of the graph are evident, right? Just look at all the degrees of various vertices. The maximum is the biggest one in that graph. The minimum is the smallest one in that graph. That's the values of those things. You can just enumerate all of them and figure out what's the biggest and the smallest. Okay, so because I want to prove a theorem here. We don't have tons of time here. Okay, so theorem 1, it's often called the first theorem of graph theory. I'm going to call it the handshaking lemma. Because that's the proof, but it says the following, that the sum of degrees in a graph G is equal to the number of edges, let me put it a little bit, equal to twice the number of edges in G, okay? So if I look at the graph and add up the vertex degrees, then I'll get a number that's 2 times the number of edges. Okay, let's draw a little picture here. So like, maybe this one that we saw early in the graph, let's look at the vertex degrees. This helps with the definition anyway. The degree of that vertex is 2. The degree is 3, right? We have 3 edges going out. 2, 2, and 3 again. If I add up the vertex degrees there, I think I get, what, 12? Yeah, 12. But how many edges does that graph have? 1, 2, 3, 4, 5, 6. So 12 over 2 is 6. So at least the theorem works for that graph. It seems to be true there. And you may even see by looking at this picture why the statement's even true. I'll give 2 proofs. They're both very simple, but yeah. Let's write it in another way because this style of notation is very common here. So in other words, this definition says the following. If I sum up the degrees, my index here is over every vertex of the graph. So my index, I'm summing over every vertex in the graph here. This type of notation will be incredibly common in graph theory, right? I have a set here, and I'm enumerating all the terms there in the set, V, so I'm summing over those and computing this value for each of them. It's not uncommon to see someone name the vertices V1, V2, V3, V4, V5 up to Vn, and then take this sum as I equals 1 up to n of D of V sub I. But that's not necessary. You don't actually have to give them names. This will compute all of them there. And the theorem says that if I sum these up, I will get 2 times the cardinality of the edge set. right? E of G, remember this set here inside of these absolute value signs represents the set of edges, and this is the cardinality of it, and 2 times it. So that's just like a little different way of writing the same statement. I actually really like theorems to be written in words. I actually think sometimes it's much easier to read this and understand what it's saying as opposed to read jargon. But this one's not exactly difficult to understand. And like I said, this is incredibly common here. Okay. So I'm going to call this proof 1 and proof 2. That's going to be a point of emphasis in this class. I think learning multiple proofs of theorems is very valuable because proof techniques and methods are just as important as the theorems themselves. In fact, in a lot of ways, they're more important because if you later on want to prove a theorem, it's important to know theorems so you can apply those theorems, but it's just as important to know techniques so you can actually use that stuff to find out new things. And graph theory is full of wonderful proof ideas that are just so cool. I really hope you enjoy some of them as much as I do. Okay, so the first proof here is like, well, what happens when you sum the degrees? So adding degrees counts each edge twice. Okay, so can someone fill in the remaining part here? It counts each edge twice. Why? What is the reason that adding the degrees adds up each edge gets sort of enumerated 2 times?
It counts it twice because each edge needs to come from a vertex and also end at a vertex.
Precisely. Yeah, exactly. Each edge is between, it's a 2-element set. It has one end and it has another end, okay? You might think about how loops come into play there and why we define loops in the fashion that we did. But yeah, so once for each edge, end. Once for, the button. Each end. Oops. End vertex, we'll call it. Sometimes the 2 vertices in an edge, we call them the end vertices, although there's no vertices but end vertices, but anyway, we use that term there. Okay, so that's the first proof. It hardly seems necessary to give a second proof if the first proof is so easy. But the second proof here I want to give because it emphasizes a proof technique that you may have seen in a combinatorics or discrete math class, but that's very powerful in graph theory. And basically is another way of stating the argument above here, just sort of overly formalized, but it will be helping, okay? So this is a new technique. So the idea is called double counting. Okay. And the idea of double counting, okay, I'm going to finish this theorem and then we'll wrap up class. I didn't realize how little time we had here. So the idea of double counting is that if you count an object twice and get a different number both times, those 2 quantities must be equal to each other, right? If you counted something in 2 different ways and you got 9 in one way and you got 8 plus 1 in another way, well, those 2 quantities have to equal each other. Now, for counting something that there's 9 of which, you don't need 2 ways to count, but if it's an abstract thing, it's very helpful here. Okay, so let's just real quick count number of pairs, the pairs being E and V, such that E is an edge and V is in E. Okay, V is a vertex. Okay, and we're working on our graph here. And when I double count a pair, especially, I do it in the following 2 ways. I figure out the number of ways to pick E, and then figure out the number of ways to pick V, subject to the fact that E was already picked. That's one way to count these things. The second way is to count V, and then count the number of ways to choose E, subject to the fact that V was already picked, right? So just like a 2-step process here. And you can go forward and reverse, okay? So in the first way, how many ways can we pick E? Well, there are E of G many edges, so there's that many ways to pick my edge there. Once I've picked my edge, how many ways can I choose the vertex? Well, 2. Each edge contains 2 vertices, so I can choose V to be the left-hand side or the right-hand side of the edge. This is a fallacy. There's no left and right-hand side, but there's 2 choices for the vertex. So that's count number 1. Great. That actually is nice because that looks like something in my theorem. The second way is I choose my vertex. Now, there's technically V of G many ways to choose my vertex. Unfortunately, unlike the above here, when I choose my vertex, the number of choices for the edge is not fixed. That varies, right? If I choose a vertex V in I don't know how many ways, what's the number of choices for E after I've chosen V? Maybe someone tell me real quick.
The degree.
The degree, exactly, right? So I fix v, there's d of v choices. But I can't multiply, like this is wrong. Something like this would be wrong, because I'd be saying d of v is fixed for every single vertex, but d of v varies. So instead of doing a multiplication here, oh, wrong button, I need to do a sum, where I take the sum and over every vertex of g, v of g, I compute the degree, right? So I choose a vertex, I don't know how many ways, but there's this many ways, d of v ways, so each one gets represented, and each time I compute its degree. So that was the number of choices for E. So this sum here also counts the number of pairs here. And this is the end of the proof, because I've said that this number of pairs here is equal to this number and simultaneously equal to this number. The consequence being that this number has to equal this number here, okay? So you can see that this is a cute little trick for showing these two things are equal to each other without ever really connecting the two directly, right? We counted this other pair, which it wasn't totally clear what this had to do with anything. Later on, when we do more sophisticated versions of this, it gets wild. It's like complete magic that you get inequalities or equalities. Okay, so I've held you guys a minute over here, so I think we can wrap it up.